number D1, Dr. Peyam. Alright, thanks for watching, and as you're watching this, I'm turning 31. I know, sad, but yay, it's a prime number. And for today, I have something really special planned. And I know there's been someone that's been waiting for this video for 1 year already. So this is for you. You know who you are. So today, what I'm gonna do, I'm gonna show that E is transcendental. So not only that it's irrational, but also that it's transcendental, which is a much stronger statement. And for this, first of all, it's a really cool proof, but it's very non-intuitive. It's due to Hurwitz. Haha, es ist so ein Witz, if you speak German. Okay, but it involves actually nothing more than calculus. So let me prep you for this a little bit. So before I state, that E is transcendental, let's just do it for general polynomial. So that F be a polynomial of degree R, and R will be to be determined. This is TBD. In fact, we'll never really determine it because it's not so important, but let F be a general polynomial of degree R, and consider the following really cool function. So capital F of x, it has nothing to do with the antiderivative, is simply the following. Take F, add its derivative, add its second derivative, ooh, how fun, etc., up to the rth derivative. So f of r of x. Okay. So suppose you're just playing around with this. Let's see what we get. And in particular, it turns out there's a nice property of this capital F. Namely, suppose you multiply this by the following integrating factor, e to the minus f of x. Let's see what we get. So let's use the product rule and the chain loop. So the derivative of that is minus e of minus x, capital F of x, and then plus e of minus x, capital F prime of x. And it turns out, you'll see there's a nice relationship between capital F and capital F prime. So first of all, let's factor out e of negative x. So it's negative f of x plus f prime of x. Okay, and now let's calculate this e of negative x of, so minus f prime, minus f double prime, etc., minus f of r. Like Guy Fieri, lots of f's, okay? And let's calculate now the derivative. So plus f prime, plus f double prime, plus f triple prime, etc., plus, plus f of r, plus f of r plus 1. And you see there's already this very nice cancellation. F prime cancels out here, f double prime, etc., f the rth derivative. And lastly, it turns out this term is also 0 because remember, f was a polynomial of degree r. So for example, if you take a quadratic polynomial and you differentiate it 3 times, you get 0. Because derivative of x squared is 2x, derivative of 2x is 2, derivative of 2 is 0. And similarly for cubic polynomials, if you differentiate it 4 times, you get 0. And if you differentiate a poly of degree r plus 1 times, you also get 0. So this disappears. And what you're left with after this huge explosion is simply minus e to the minus x, f of x. So it's really cool. In other words, if you differentiate this huge thing, it's as if you just differentiated capital F, except maybe with a minus sign. So in some sense, up to this, conjugation by e to the minus x, you do get, an antiderivative. in some sense. And we will use this actually now. So that was the prep work. Let's do a little bit more of prep work, because since you have this nice identity, about differentiation, maybe we should use the mean value theorem. And let's see how that goes. So, again, it's not an intuitive proof at all, but it's really cute. You'll see. It's like as delicious as my birthday cake. So, step 2, and remember, e of minus x, f of x. If you differentiate that, you get minus e of minus x, f of x. Okay, now take this function and apply the mean value theorem on the interval 0, 1. So mean value theorem of e to the minus x, f of x on 0, 1. What does that give you? Well, remember, mean value theorem says f of 1 minus f of 0 over 1 minus 0 equals to f prime of some constant. So in this case, e of minus 1, capital F of 1, minus capital F of 0 equals to the derivative of that, which is, divided by, again, 1 minus 0, equals to the derivative of that, which gives you minus e of minus c f of c, but let's just rewrite this as minus e of minus, because we'll have many names for constants, let's just call it theta 1, f of theta 1, for theta 1 between 0 and 1. And let's clean this up a little bit. So if we multiply both sides by e, you get f of 1 minus e f of 0 equals to minus e of, again, you multiply this by e, so 1 minus theta 1, f of theta 1. And this huge constant, let's call it epsilon 1. And we'll need this very soon, actually, in the next step. Okay, so that was so much fun. Let's do it again. And let's apply the mean value theorem now on the interval 0, 2. So that was on the interval 0, 1. Now let's do it on 0, 2. So e of minus 2, f of 2, minus f of 0, again divided by b minus a, which is 2, equals to, again, f prime of some constant, which in this case is minus e of, again, minus a constant, f of some constant. Ideally, we'd like to have something between 0 and 1, so up to renormalization, just write it as minus 2 theta 2, f of 2 theta 2. If you'd like, you can just think of it as minus c2 f of c2, and then just let theta 2 to be that constant divided by 2. So again, where theta 2 is between 0 and 1. And again, let's clean this up. Multiply by 2, and then by e squared, and you get f of 2 minus e squared f of 0 equals to minus 2 e of 2 minus 2 theta 2. So let's just factor it out as e of 2 of 1 minus theta 2 f of 2 theta 2. And again, let's call this epsilon 2. And again, let's see, where's my color at? So notice there is some, similarity between those two terms. Right? This is minus 1 e of 1 times 1 minus theta 1, minus 2 e of 2 times 1 minus theta 2. And you can guess, on a general interval 0, n, the whole thing just changes to n. So, again, n will be to be determined very soon. To TBD. Okay. TBD, not to be confused with TVD, The Vampire Diaries. Okay, so on the interval 0, n, you get f of n minus e to the n f of 0 equals to minus n e to the n times 1 minus theta n f of n theta n. And let's call that epsilon n. Again, where theta n is between 0 and 1. Okay, great. We defined our cute function capital F. We played around with the mean value theorem, and that was our prep work. And now let's actually use our proof. So let's start our proof, and you'll see all that stuff will be super useful. Okay, so step 3. Here's a, here starts the proof where E is transcendental, and it's almost always done by contradiction. So let's suppose E is algebraic. In other words, suppose that E is a root of a polynomial with integer coefficients. So suppose we have some polynomial Cn e to the n plus etc. plus C1e plus C0 equals to 0. Okay. Where, so in other words, suppose E is a root of a polynomial with integer coefficients. So Ci is an integer, and you may object, you may say, hey, what about rational coefficients? Turns out, just by multiplying the polynomial by a huge number, you can make all those coefficients to be integers. So no loss of generality here. And moreover, if this is negative, then just assume that just multiply by -1 and you get a positive number. So C0 is positive. And if it's 0, just take that polynomial, factor E out, and divide by E. And then you get the same spiel, where you can assume that coefficient is positive. And this will be useful later. I don't quite remember where, but very soon we'll see. Okay, so suppose E is a 0 of a polynomial. Let's play around with these coefficients a little bit. And in particular, now let's merge this with step 2, and let's combine those with those epsilon n's. And you'll see there's something nice going on. Because C1 epsilon 1 plus ... plus Cn epsilon n. Now, yes, that was the definition of epsilon n, but we're more interested in this thing here. And it's normal that it didn't put C0. You'll see it in a second. So, what was epsilon 1? Well, it sort of was f of 1 minus e of f of 0. And then epsilon 2 was like f of 2 minus e squared f of 0, etc. So plus C2 f of 2 minus e squared f of 0 up to epsilon n, which is f of n minus e to the n f of 0. And by the way, remember I said n is to be determined. Well, it is determined here because n is just the degree of the polynomial. So it is fixed now. And let's take that now, expand it out. So what we get is C1 f of 1 minus C1e f of 0 plus C2 f of 2 minus C2e squared f of 0 plus blah 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 plus Cn f of n minus Cn e to the n f of 0. And now let's group a bunch of those terms. In particular, let's see, let's group the C1 f of 1, C2 f of 2 terms together. So what we get is C1 f of 1 plus ... plus Cn f of n. And the nice thing is, here, for the other terms, we have a common factor of f of 0. And so let's just factor it out. In fact, let's factor out minus f of 0. And we get C1e plus C2e squared plus dot 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 plus Cn e to the n. And now here comes something truly beautiful, because what were the C1, C2, etc. up to Cn? Well, they were exactly the coefficients of the polynomial. So in particular, C1e plus C2e squared plus Cn e to the n, well, that equals to minus C0. So this whole thing is just minus C0. So it turns out this weird term actually groups pretty nicely with this term, because minus C0 times minus f of 0, that's just C0 f of 0, which just sticks around, at the head of this. So what we get in the end is that if you take this linear combo of epsilon i's, C1 epsilon 1 plus blah 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 plus Cn epsilon n, that's just the same thing as C0 f of 0 plus C1 f of 1 plus dot 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 plus Cn f of n. Again, super cute identity, but if you're wondering what's going on, it's completely normal. As I said, it's a super non-intuitive proof, and you may say, and you'll probably be confused till the end, okay? Just like I'm confused that I'm 31, okay? Take some time to digest. So far, again, super cute, super like, what the hell is going on? But let's not do it for a very specific polynomial, because so far all the results held for any polynomial of degree r, basically any polynomial of any degree, and let's now choose a very specific polynomial. So step 4, let P be a huge prime. We'll select it at the end. It almost goes to infinity. So think of it as very big. So it's bigger than n, which is again the highest degree of the polynomial in E, okay? And it's also bigger than C0, which was that constant term in our expansion of E. So let P be huge, be bigger than n, bigger than C0, and P is prime. And this will be super important later on. And consider the following polynomial. So let f of x be 1 over p minus 1 factorial, x to the p minus 1, 1 minus x to the p, 2 minus x to the p, etc., and n minus x to the p. Okay, what is going on? Imagine this is true, and as before, let capital F be just this cute sum of derivatives, f of x plus f prime of x plus dot 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 plus f to the r of x. And remember before we didn't know what r is? Well, r here is just the degree of f. Which, let me see, it's probably like p minus 1 plus np. So it's a fixed number now, so we're happy. And now we want to say, well, with this polynomial f, what are some of the properties of capital F? And turns out there's some nice properties that help us conclude. So, first of all, claim 1. What happens if you evaluate capital F at integers? So for j equals to 1 up to n, f of capital J, again, there is this huge number here, p minus 1 factorial. It's not even clear that it's an integer. It turns out it is an integer. So is an integer. And moreover, even cooler, it has to be a multiple of p. Of p. And why? It's not really intuitive, but the way to do this is by cases. So remember, f involves sums of derivatives of f's. And the question is, on the one hand, what happens if we just take a couple of derivatives? And on the other hand, what happens if we take a lot of derivatives? So, why did I build f like that? Notice that this polynomial has roots at 1, 2, 3, up to n. And not only that, it has a lot of roots. Right? Like 1, it has a root p times. 2, it has a root p times, etc., etc. So, on the one hand, so f has a root of multiplicity p at 1, 2, n. In particular, well, if it has a root, if you evaluate it, f at that root, it has to be 0. Right? So in particular, for j from 1 to n, well, f of j equals to 0. That's just by definition of a root. Moreover, what happens when you calculate the derivative of f? Well, it's a huge product rule, but because we have a root of multiplicity p, where again p is huge, you will still have a root. The derivative will also have a root. Because the worst thing that happens is that, for example, you get p 1 minus x to the p minus 1 times minus 1. If you evaluate it at 1, this 1 minus x to the p minus 1, it's still 0. And same for the second term up to the nth term. So we even have f prime of j equals to 0. And not only that, it turns out if you do it again, you're still okay. Again, you would just use another huge product rule. And it turns out you're safe up to the p minus 1 derivative. So it's still 0. At p, you have some issue because, for example, this will become 1 minus x to the 0th power. So it's not clear that if you plug it in at 1, you still get 0. So the point is, if you take few derivatives, you're still fine. And the question is, what if you take more derivatives? And it turns out you won't really have 0 anymore, but it's fine because what we want to show is that it's an integer. We not necessarily want to show that it's 0. So, and again, let me leave this little f. Now, let's see what happens when we take more than p, like p derivatives or more. Suppose we expand out f, okay? So what we get is, notice, well, f of x, well, the smallest term is x to the p minus 1 if all those things are constant. So imagine you FOIL out this huge polynomial, then what do you get? You get here 1 to the p, 2 to the p, etc., up to n to the p. And again, we want the smallest term, so let's forget about the x for a second. And what this becomes, it's 1 times 2 up to n to the p, but that's just n factorial to the p. So if you FOIL out f, then the lowest order term becomes n factorial to the p, okay, divided by, of course, p minus 1 factorial, x to the p minus 1, okay. And then higher order terms, and we don't really care about those, so, for example, some integer over p minus 1 factorial, x to the p, and then some other integer over p minus 1 factorial, x to the p plus 1, etc., Okay, so I think we're good. We don't need that definition anymore. And again, lower order terms are 0, so that's good. And the question is, what if we differentiate f a lot of times? So, greater or equal to p. What happens is if you take a lot of derivatives, okay, then either the terms will cancel out, or you will take so many derivatives that the resulting coefficient will still be a multiple of p. So let's maybe illustrate this for f of the pth derivative. First of all, again, this term disappears, and then we get a0 p times p minus 1 times 1 over p minus 1 factorial, and then plus a1 over p minus 1 factorial at p plus 1 times 2 times x plus . First of all, here the nice thing is we get a cancellation. So this is really p factorial over p minus 1 factorial, which is p. And then what happens here, we get, let's see, like p times p plus 1 times p. And same also with the other terms. So it turns out that if you take p consecutive integers, like the multiplication on it, and you divide it by p minus 1 factorial, you still get a multiple of p. So what happens then is that fp of x becomes a polynomial whose integers, whose coefficients are divisible by p. So yes, fp of x is a polynomial with coefficients multiples of p. And it turns out the same thing is true if you take higher derivatives. So let's just do it for I greater than or equal to p. So fi of x is a polynomial with coefficients multiple of p. And so in particular, if you plug it at integers, so fi of j, so j from 1 up to n, you have that it's a polynomial that has coefficients that are multiples of p. And so the nice thing is, if you then just add them together, what do you have? You either have terms that are 0 or terms that are multiples of p. So fi of j is a multiple of p. So in the end, again, just to summarize, we have the following. So f of j, which is again f of j plus f prime of j plus plus f to the p minus 1 of j plus f of p of j plus plus f of r of j. again, all those terms are 0, and those terms are just multiples of p. And so in particular, f of j is a multiple of p. And in particular, it's an integer. And again, it's not obvious because this little f, right, has this huge denominator, so it's not clear that it's an integer. But it turns out if you just add everything, you know, then you do get, and you evaluate it integers, then you're fine. Okay, and the question is, again, what the hell is going on? We're almost, well, we're like halfway done actually, but why did we really care about this? Well, we had this linear combination, right? C0 f of 0, C1 f of 1, up to Cn f of n. And we sort of took care of the case, you know, C1 f of 1 and Cn f of n. And there's just one case remaining. What about f of 0? So, claim 2. Turns out, even though it's body f of j, or n bodies f of j, they're integers and multiples of p, it turns out that f of 0 is still an integer, but not a multiple of p. I like to remind you, what was f of x? Well, f of x, at least the expansion was, I guess, n factorial to the p minus 1 factorial, x to the p minus 1, plus other terms, blah x to the p plus dot dot dot. Okay, and again, you do it by cases. What if you take lots of derivatives? What if you don't take many derivatives? So on the one hand, well, if you evaluate f at 0, you get 0 because of this x to the p minus 1. And same, if you take just a couple of derivatives, because of this x to the p minus 1, you still have, 0. So f prime of 0 equals to 0, dot, 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 up to, I guess the evil term is p minus 1. So if you still take p minus 2 derivatives, you're good. But the question is, what happens when you take the p minus first derivative? Well, what happens here is that you get p minus 1 factorial, and then just terms involving x and x squared. What is f to the p minus 1 of x? Well, it becomes, I guess, n factorial to the p times p minus 1 factorial, which cancels out here, plus, again, blah, different blah times x, plus other blah times x squared, etc., etc. And in particular, if you evaluate this at 0, you get 0, 0, 0, except for n factorial to the p. So f to the p minus 1 of 0 is n factorial to the p. However, remember that p was huge. Right? P is greater than n, and p is prime. So in particular, what happens here is we have factors n times n minus 1, etc., that are smaller than p. So in particular, p cannot divide this at all. Take, for example, the number 13. It's a huge prime, and it cannot divide, all the numbers up to 12. Otherwise, I guess it wouldn't be prime or something. It wouldn't be bigger than 12. So in particular, what happens, and The fact that it's repeated p times, it doesn't really matter, because if like 13 doesn't divide 2, it doesn't divide 4 or 8 or 16 anyway. So even though this is a gigantic number, p doesn't divide that number. Which is good, because we want to show that ultimately f capital F of 0, it's an integer, but not a multiple of p. And lastly, what happens if we evaluate this at higher derivatives? Well, then we're actually good. Again, by the same fact as before, what we have is that the ith derivative of f, remember what we showed? It's a polynomial whose coefficients are divisible by p. Are divisible by p, or I guess multiples of p, same thing. Again, for the p derivative, you have a p times this thing, and here also, remember you had a p times p minus, I guess p times p plus 1 or something was also okay. So in particular, if you evaluate it at 0, just have, I guess, the constant term, which again we saw it's a multiple of p. So this thing is also an integer divisible by p. And so what do we have? Well, remember, capital F of 0, by definition, is the sum of derivatives of f's. So f of 0 plus the p minus second derivative of f at 0 plus the p minus first derivative of f of 0, and the higher derivatives f of p of 0 plus dot 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 plus f of, again, whatever this r is, the degree of f. Now, what have we shown? We've shown that, well, p divides that. Okay. P doesn't divide this number, and p divides this number. So what do we have? We have a sum of a bunch of terms that are divisible by p, but this one term that's not divisible by p. So in particular, if you take the sum of all that, it's not divisible by p. Great. So I'm also confused right now. Let's see what have we shown so far. This is very good because we've shown that if you evaluate capital F at 1, 2, 3, up to n, it's divisible by p. If you evaluate at 0, it's not divisible by p. So let's see what happens when we take the linear combination. If you're still watching, respect. Again, it's a cool story. It's like going in a tunnel and then you have no idea what's going on. And suddenly you go out of the tunnel and like everything becomes clearer. So it's like a little dungeon, I guess, okay? Okay, so in particular, again, what happens when we take the linear combination C0 f of 0 plus C1 f of 1 plus dot 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 plus Cn f of n. Remember, p divides f of 1. So in particular, it divides a multiple. So C1 f of 1. So p divides that. And same thing for here. Okay. Now we also know that p doesn't divide f of 0. It's possible that it divides C0, that p divides C0 and then it divides the product of this. It turns out that it doesn't. And remember, that's because at the very beginning, I said that p is greater than C0. And that's actually super important. Because if p is a prime that's greater than c0, it can't divide this. And because p is a prime, there's no way it could divide a product. Because if p is a prime, it would have to divide this, or it would divide this. But it's not possible. So in particular, p doesn't divide the whole thing. So it doesn't divide c0 f of 0, and because the rest is divisible by p, what we know is that this whole thing is an integer not divisible by p. And that's very, very important. It's an integer not divisible by p. Okay, so it's integer and it doesn't divide p, which would be a problem, for example, if it's 0. If we somehow show this is 0 or like 1/2, we have a problem. Aha! And this is actually the crux of the argument. Because remember, in a galaxy far, far away and long, long time ago, we've showed the following. So we're sort of going to the crux of the thing. Because why did we care about this linear combination, c0 f of 0 plus blah, 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 plus cn f of n? On the one hand, it's not divisible by p, but remember, this also equals to this weird linear combination of the epsilons, right, that we got from the mean value theorem. And here's the thing, we will show that if we choose p very large, this will not be an integer anymore. And so in particular, p cannot divide this. Okay, and we're almost sort of at the crux of the proof. Because why did we care about this? Because remember, a long, long time ago in a galaxy far, far away, we've shown that this quantity equals to c1 epsilon 1 plus dot, 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 plus cn epsilon n. Here's how we're going to conclude. If we somehow show that this is sort of strict, like very small, let's say if we show that this is 1/2, what's the problem? Because on the one hand, this is 1/2, but because this is an integer, it will actually have to be 0. What are we going to show? Suppose we show that this is somehow less than 1/2 in absolute value. Well, if this is an integer, because this is less than 1/2, it would have to be 0. But that's a problem, because if this is 0, since 0 is divisible by p, this would mean this is divisible by p, which isn't. And that would conclude, they would give us a contradiction with what? With the fact that E is algebraic. All right, so let's do that. So we'll show this equals to 0. I guess we'll show it's like, let's say, less than 1 in absolute value. Okay? And for this, let's remember what our epsilon's i's were. So epsilon I, again, long time ago, that was minus I e of I times 1 minus theta I f of I theta I. Or again, theta I is between 0 and 1. And now, let's remember the definition of f, because that's super important. That's minus I, e of I, of 1 minus theta I. Now f, it had to be divided by p minus 1 factorial. And then it was this x to the p minus 1, so I theta I to the p minus 1, and then 1 minus that, I theta I to the p, up to n minus I theta I, p. Okay. And now I guess let's estimate this. So, absolute value e to the minus I. So, on the one hand, well, this p minus 1 factorial, it's still p minus 1 factorial. This thing in absolute value, remember I is just between 1 and n. So worst case scenario, this is n. And also, remember theta I was between 0 and 1. So this is between, also between 0 and 1. So if you multiply this by I, it's strictly less than I, and just very, roughly it's less than n. So this is e to the n. And again, very roughly, this is strictly less than I, and this is strictly less than n. So this becomes n to the p minus 1. Again, no fancy analysis involved here. Just, very rough estimates. This is strictly less than 1. So the whole thing strictly less than 1 to the p. And this is n to the p. And in particular, if you put that together, just like before, you have 1 up to n to the p. So n factorial to the p. And so if you combine this, the whole thing becomes, so e to the n factorial to the p, okay. And n to the p minus 1 times n becomes n to the p. Like that, it looks like a huge term, but remember, we divide this by p minus 1 factorial, and remember, p was a huge prime. It's way, way bigger than n, so it turns out, if you take the limit of this as p goes to infinity, in other words, if you take p to be very, very large, this goes to 0. Okay. If you're not convinced, let me give you a quick argument why this is true. This sequence, let's call this AP. Because again, n is fixed here, and we let n go to infinity, and so we get that p goes to infinity. And in particular, suppose you consider the ratio of successive terms. What happens is that we get e to the n factorial to the p plus 1, n to the p plus 1, over p factorial, divided by this, so you just flip it, p minus 1 factorial over e to the n factorial to the p, n to the p. Now, there's a nice cancellation. This cancels out. The n factorials cancel out except for one term. The n to the p's cancel out except for one term. What we're left with at the end is just n factorial times n over p. And if p is very large, remember p is much bigger than n, we can in fact make this less than 1/2. And why is that cool? Because if you now use the ratio test from calculus, what you have that is that the series of APs goes to infinity, converges. So in particular, by the divergence test, you have to have that AP goes to 0 as p goes to infinity. So in particular, what we have is that epsilon I is less than equal to e to the n factorial to the p, n to the p over p minus 1 factorial. and as p goes to infinity, this goes to 0. But we don't really want to let p go to infinity. We just want it to be very large. However, this is enough because if p is very large, we can make this very small. And in particular, we can make this term very small. C1 epsilon 1 plus dot 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 plus Cn epsilon n. By choosing p large enough, because there are only finitely many terms, we can definitely make this less than 1 in absolute value. But here comes the crux. This is actually equal to, remember, or I guess C0 f of 0 plus dot 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 plus Cn f of n. But remember, this thing was an integer. So if we have an integer that's less than 1 in absolute value, it has to be 0. So 0, 0 plus f of 0 plus dot 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 plus Cn f of n equals to 0. And the contradiction lies in the fact that we know that p doesn't divide this number, but the number is 0, and p definitely divides 0. And so we cannot have p dividing 0 and not dividing 0. And that's a contradiction. A contradiction with what? With the fact, with the assumption that E was algebraic. And therefore E is transcendental, and we can go home very happy or very confused, maybe. Anyway, if you like this awesome excursion into math, please make sure to subscribe to my channel. Thank you very much.